This is lecture number 43 of the course ME314 Fluid Mechanics 2, and this is the third lecture of this week. We have already started CFD, and today we will go into the finite difference method. So, an overview of the numerical methods like finite element, finite volume, and finite difference. We will focus on the simplest one, the finite difference method. There are different types of schemes used: forward difference, backward difference, and center difference. We will look into the first derivatives, second derivatives, and the mixed derivatives as well. We will solve a problem using the finite difference method, and then we will look into the solving the problem of using ANSYS-CFX, the software, which I will explain in the next two lectures. So we have the fluid flow problem, or any physics problem. Physics of the problem is determined by the governing equations, and these governing equations are the partial differential equations. So what we need is, these are continuous in domain, so what we need is to convert these continuous domain into discrete domain. And so we will be able to turn the partial differential equations into a set of algebraic equations. So this method is actually called as discretization. This discretization have several different types of approaches. Here I have mentioned finite difference and finite volume. So in finite difference we will look closely today. In finite volume method, we take a finite volume and we observe the governing equations to be satisfied within that volume. So what is happening in the volume is dictated by what is coming in and what is leaving the volume. So once we turn our physical problem from PDE to the set of algebraic equations, so these algebraic equations can be solved through some numerical methods, and so we will be able to, the solution is we will be able to get the variables of our interest. For example, in momentum equation and continuity equation, the variables are the pressure and the pressure distribution as well as the velocity distribution. Finite difference is the easier method, started earlier, and it is usually applied to a grid which is a structured grid, and we will look in the later part of this lecture, not today's lecture but in the next lectures, about what is actually structured grid. So in finite volume method, which people started recently, and here we are interested in observing the conservation equations in that finite volume. And since the shape of the domain is not that important, because we are dealing with what is happening at the inlets and at the outlet, the surfaces of the finite volume. So we just observe the conservation to be maintained within the volume. So that's why, compared with finite difference, this technique is capable of dealing with any type of grid. In finite element is a technique in which one can handle complex geometries, and but computational resources it requires more computational resources. So all these techniques today we will focus on the first technique, that is the finite difference method. Finite difference started earlier, and it is actually the differential equations people used to solve it, to convert it into algebraic form, and before the advent of computers, these set of equations to be solved through hand calculation. But once we have the ability in computer to solve large set of equations, so this method can be done through computers as well. Taylor series expansion is actually used to generate a finite difference approximation to the partial derivatives. In this way, we will be able to get information of our variable of interest at each grid point. So let's say we have arbitrary variable phi is just an arbitrary variable here, and we are interested in getting information about the point I plus 1 comma j, because we are expanding the Taylor series at point ij. So once we are interested in one step forward from I to I plus 1, then we can write down the first term of the Taylor series, and the second term has a first derivative, third term have second derivative, and fourth term have higher order derivatives, and so on. So this would be the any flow variable phi at a point I plus 1 k, I plus 1 comma j can be expanded. So what we need is, in order to get information about at the point which is 1 unit in the forward direction, we need a knowledge of the variable at the point before that variable. So ij would come first and then I plus 1 comma j. So let's say if I am interested in getting information at I plus 1 comma j, I need to know what is happened at I comma j. So this information is needed in order to predict the information at the forward point. What I can do here is I just have brought the first derivative on the left hand side, and just to rewrite the same equation number 1. Here the higher order terms we call it to be as a truncation error. So we just approximate the first derivative with this difference of the terms. So the first derivative of phi with respect to x can be evaluated. If I am interested in evaluating the derivative at that point, I need information about the forward point and the information of that variable at that ij point. Then I will be able to calculate the first derivative, and this truncation error is actually represent which is an order of the delta x. If delta x is small, then delta x square is much smaller, delta x cube is much smaller, so all these terms can be ignored. So then we can write the first derivative in terms of the finite difference equations. So since we have, in order to calculate the first derivative at point ij, I need an information about the forward point. That's why it is called as forward difference. And since the order of accuracy is the delta x is the order of accuracy, so it is actually called as first order accurate. Same thing, if I do it, I am interested in calculating information about point behind I comma j, that is the backward point I minus 1 comma j. So I expand the Taylor series accordingly. So I have now the one term negative, one positive, one negative, and so on, so on. So from that equation, if I just bring the first derivative on the left hand side and another term on the right hand side, so it is exactly the same thing by as we have done in the forward difference, but in order to calculate the derivative at that point, I have taken information of the backward point. In the previous, we have taken information about the forward point. In order to calculate the first derivative at point I comma j, we need information of the backward point, and here the order of accuracy for truncation error is also first order accurate. So this difference is called as the finite difference, where the first derivative can be represented in terms of finite difference equation. And in order to calculate the derivative at point ij, I need a knowledge of the previous point. That variable, I must have the information of that variable phi. This variable phi could be anything, velocity, it could be pressure, it could be temperature, it could be any variable. So I must have a knowledge of that previous point so that I can calculate the derivative at that point I comma j. So we have dealt with the first derivative. So the first equation for forward difference is this. For the second equation, which is for use for backward difference, is the equation number 2. What now I can do is I have the information of the forward as well as the backward. So I subtract equation 2 from equation 1. So what I have done is by subtracting these two equations, I got this expression, and now I need to bring the first derivative on the left hand side and everything on the right hand side. So if you bring it like that, it means here if you divide by delta x, and this order of accuracy would be delta x square. So this is actually called as central difference method, because in order to calculate the derivative at point ij, I need more information. I need information about the forward point, I need information about the backward point. So this difference is actually called as central difference. So once, in order to calculate the first derivative in the information of the forward point, that is called as forward difference. If you need information of the backward point, that is called as backward difference. If you need the information about forward and backward both points, then it is called as central difference. And we have seen that if you divide by delta x on this side, so you got 2 here and as well as delta x whole square. So it means the more information you need in order to calculate the derivative, and the advantage is to have more order of accuracy. So it is second order accurate compared with the forward and backward difference. Second order derivative can be worked out using this Taylor series extension. So what I have done is I have calculated the first derivative using forward difference, backward difference, and central difference. Now I am interested in second order derivative. So this I can do it because in previous case I have subtracted equation 2. Now I add equation 1 and 2. So once I add equation 1 and 2, then this negative and positive terms cancel out. So I got that thing. So the first term I got is the second order derivative. I just brought the second order derivative on the left hand side and everything on the right hand side. So I got the expression for second derivative of that variable of interest phi, which requires knowledge of that variable at the forward point, backward point, and at the point where I am calculating the second derivative. And once you divide by delta x whole square, then this would be second order accurate. So second order partial derivatives comes out, or automatically comes out to be second order accurate. Once I have done it, the same thing I can do it for if I move in the y direction. If I am at point ij, I move to point ij plus 1 by traveling distance delta y, or this backward. So I can get the first derivative for y, for similarly for backward difference, and similarly for center difference. And similarly, we can do it by second order partial derivatives. So this is similarly we have worked out, as we have worked out dou phi by dou x. Now we can, by same procedure, we can work out dou phi by dou y. So the next question comes about mixed derivative, because your partial differential equations would be in such a manner where your velocity or any variable of interest would be having not just first with respect to x, but we have derivative with respect to y as well. So such derivatives are called as mixed derivatives. So just take use of equation number 1, we have already formulated. So here I need to differentiate equation 1 with respect to y. So I have differentiated here with respect to y. So I got this equation number 3. So tau phi ij with respect to y. So with respect to x, then differentiated, so with respect to y is there. Already tau x square, then with respect to y. So I have just differentiated equation 1 with respect to y. Now the same thing I have to do it for equation number 2 earlier. I differentiate again with respect to y, that equation number 2, I got equation number 4. So I have forward point, backward point in x, forward point in y, and backward point in y2. So from equation 3 and 4, if I just subtract equation 4 from equation 3, I will be able to get that expression. And here I have this mixed derivative, just bring on the left hand side. So if I know the first derivative of that function phi with respect to y, I can calculate that mixed derivative. I just substitute the finite difference expression. So in this way, I will be able to calculate the mixed derivative, tau square phi with respect to x and y. So here I need information about all 4 points in order to calculate that mixed derivative, because mixed derivative involves variation in x as well as variation in y, and so this can be evaluated. And since all these forward, backward, and the point where I am evaluating at ij, I am evaluating the mixed derivative, I need information about all those variables. So that's why it is called as central difference in x as well as central difference in y. And just like in one dimension, once it is second central difference, then it is automatically second order accurate. Okay, now let's see how we need to use such equations to solve our problem. So we have just consider a flow through a porous wall. So this is a wall which is a porous wall. So what happens is the velocity is uniform once it enters when x is 0. And when x equals to L, its velocity reduces from 9 meters per second to 3 meters per second. And what I need is, I need the value of the stream function inside this rectangular boundary. So this is the rectangular boundary, and I need to know the value of the stream function within that boundary, within this rectangular shape. So what else is given is the height of this wall is given as 0.6 meter and the length is given as 0.9 meter. So it's a two-dimensional problem. So you need to find out the value of the psi using finite difference method, and the governing equation here is the Laplace's equation because it's a two-dimensional flow. And what we can do is we can take the grid size mentioned here is 0.3 meter in x and 0.2 meter in y can be taken as a grid size. So the first thing is, since some mass is coming in to the domain and some mass is leaving, we apply the continuity equation. So as we know, when x is 0, your velocity is 9 meters per second. When x is equal to 0.9 meters, then velocity is 3 meters per second. So some change in velocity is occurring as you are moving in x direction. So that is actually represented by this term tau u by tau x. We can work out how the velocity component v, which is in the y direction, changes as you move in the y direction. So here I substitute the value of the velocity in x direction is u1 minus u2, and the distance between them, the change in that would be L is, which is the length of the wall, plus and the velocity changes in the y direction we don't know, but we know when y is 0, due to that no slip boundary condition, the velocity would be 0. So in the y direction we are moving from 0 to some velocity. We have given a name uy. So uy is actually the velocity in the y direction, which is actually 0 minus uy. and the distance change in y would be from 0 to uy is h. So h is that distance. So I just got that equation, just substituted the values in this continuity equation for two-dimensional flow. Now I simplify that, I will be able to get the velocity component v. Actually, I have used the letter u y to represent the velocity in that y direction. As I know, I need to work out the stream function, and so once the velocity is known, or if the stream function is known, if you differentiate with respect to y, you get the velocity u, or if you know the velocity components, you can work out the stream function. So here in this problem, we need to work out the stream function. So let's say if we integrate that expression, psi would be uy plus c, and here I am assuming that when y is 0, you are at here, at no slip boundary condition, your stream function is taken as 0. So once this is 0, when y is 0, then c comes out to be 0. So my stream function would be changing as I am moving in the y direction, times the component of the velocity in the x direction. So u times y would be my stream function. As I know, when your x is 0, you are at here, then your psi would be, u becomes u1 times y. So when y is 0, your psi comes out to be 0. When y equal to, let's say, 0.2 meter, so 9 multiplied by 0.2 would be the stream function at that point. And similarly, we can work out the stream function when x is 0. When x equals to L, you are at that place. We know the stream function is u times. So when x equals to L, you are here, and the stream function would be u2 times y, which is a function of y. So you know the velocity u2 is 3 meters per second, so it would be 3 times y. So when y is 0.2, then the stream function would be 3 multiplied by 0.2. So what we can do here is we divide the whole domain, which is a continuous problem, into discrete grid. So I divide, because the whole thing is 0.9, so 0.3, 0.3, 0.3, so it would be 0.9, and the whole thing in the y is 0.6, so I divide it to the grid size of 0.2 plus 0.2 plus 0.2, then it would be 0.6 meter. And I have just named the grids point as 1, 1 at that grid, so it would be 1, 2, 1, 3, and 1, 4. Similarly, 2, 1 and 2, so it would be 1, 1, because the row, this row is 1, then this is the second row, this would be the third row. Actually, it should be the column should be, actually just change the columns. Actually, it should be 1, 1, 1, 2, and only change that. But as we know that when y is 0, your stream function is 0. So at that line, your whatever your numbers are, your stream functions would be 0 here. So it would be okay. So you just give some numbers, some names to each point, because I am interested in getting the value of stream function at all these grid points. So this is an objective. As I know, when your y is 0, you are here, then your stream function is 0 here, 0 here, 0 here, 0 here. And when your x is 0, you are here, then your stream function would be u1 times y, then it would be 9 times y. So whatever y is 0.2, then 9 times of 0.2 would be the stream function here. So similarly, when x equals to L, your stream function is 3 times y. So what we can do is we can work out, and we know the velocity in the y direction, we already worked out from continuity equation is 4 meters per second. So when x is 0, your stream function is 9 times of y. So your y is 0.2. So 9 multiplied by 0.2 it would be 1.8 here. And then at this distance y is 0.4. So 0.4 multiplied by 9 would be 3.6. And here the distance is 0.6, so 0.6 multiplied by 9 would be 5.4. So you got the value of the stream function at when x equals to 0. Similarly, you can work out the value of the stream function when your x equals to 0.9 meter. So when x is 0.9 meter or L, then your stream function is 3 times y. So when y is 0.2, so 3 times of 0.2 would be 0.6, 3 times of 0.4 would be 1.2. And 3 times of 0.6 would be 1.8. So I have the value of the stream function at the boundaries because of that boundary conditions given. So I know the stream function here, I know the stream function here, I know the stream function here. I need to work out stream functions at these points as well as these 4 points in the middle. So this is something I have to work out. So let's see how we can work out at the boundary because as you know the stream function here I know that's 5.4 and I have no information about what is the stream function here. So as I know the rate of change, the change in the value of the stream function is actually equal to the volume flow rate. So if I have 1 comma 4 and I have 2 comma 4, so the change in the value of the stream function is nothing, just the volume flow rate. Volume flow rate means because one of the dimension is unity, so the change in the value of the stream function is actually equal to the volume flow rate, which would be meter per second into meter into 1 meter, then it would be meter cube per second actually. So even if it is not mentioned, then you can write the units to be meter square per second, because meter per second multiplied by meter would be meter square per second. So that would be the change in the value of the stream function. So what I know is, I know information at 1 comma 4. I can work out information at 2 comma 4 because these two values are known to me. So stream function at 1 comma 4 is already, we have worked out 5.4, and stream function at 2 comma 4 is unknown, and velocity in the y direction is 4. So and delta x is 0.3 meters. So the velocity stream function at 2 comma 4 I have worked out comes out to be 4.2. Similarly, I can work out stream function at 3 comma 4 as well. So stream function at 2 4 minus 3 4 would be the velocity in the y direction times the distance. I substitute the value of stream function 2 4, which I have already worked out, 4.2. So the only unknown here is the stream function 3 comma 4. So I know these two values of the stream function at the boundary as well, just applying the fact that the change in the value of the stream function we have already seen in the potential flow theory. The change in the value of the stream function is actually equal to the volume flow rate. Now I need to solve my fluid flow problem for these 4 nodes, and my governing equation is a Laplace's equation. So what I need is this Laplace's equation to be applied to the grid. And as I know from finite difference method, the second order derivatives, because I am dealing with the second order derivatives of some function in x as well as in y. So I just use these expressions. So instead of phi, I just replace with psi. So that would be psi I plus 1 comma j minus 2 psi I comma j and psi I minus 1 comma j. So that would be my governing equation, which I have using this finite difference method, I turned this partial differential into algebraic equation. This equation I can simplify just dividing by this equation by delta x whole square. So I got this. Further simplify, I can write same equation like this. So this is something, a generic equation which fits for any point I comma j. So if I know the stream function at I comma j, I need to put those neighboring points here. So I get that equation. So now let's see what I do it on this grid. I know this equation for the point 2, 2. So for that point 2, 2, I know that ij is my point 2, 2. So that is my psi 2, 2. And I just substitute, I know the value of delta x and delta y. And stream functions at 3 comma 2 is not known to me, but I know the stream function at 1 comma 2. So 1 comma 2 would be 1.8, and delta x over delta y whole square would be 2.25, and stream function at 2, 3 is not known, but a stream function at 2, 1, that is 0 here. And the whole thing you work out would come out to be 6.5 minus 6.5, and this would be the stream function at 2, 2. I got that equation. Same thing I do for other points for point 3, 2, and I got that equation. Similarly, I got the same thing for point 2, 3, and the same thing for point 3, 3. I just substituted all that. So I got these 4 equations. So once we solve all these 4 equations, we will be able to get the value of the stream function at those 4 points. That is something we have to work out. So this example shows how the finite differential method is used to solve that problem, because our variable of interest was the stream function in that case, and boundary conditions were given, and we have a governing equation in a partial differential form. Using the finite difference, we turn it into a algebraic set of equation, and then we need to solve that algebraic set of equations using any matrix or any technique. So we got those values of that unknown. So this is how the finite difference method works. I mean, in the next 2 lectures, I will talk about ANSYS-CFX. Just give you a little brief overview of ANSYS-CFX. Actually, it has a 5-step journey rather, and there are 4 softwares associated. One of the software called ICM is actually dealing with first building a geometry and do the meshing. So the whole thing can be done in one software called ICM. So such a grid can be developed on ICM. And then you need a CFX trees where all the physics to be supplied, what type of analysis it is, what boundary conditions are. So whole physics to be implemented in CFX tree. Once you have made your problem, now you have to go to the solver to solve that problem, so you get some solutions. Once you got the solution, these solutions to be represented in the form of some graphs or some visuals, so that is actually called as CFX post. So in ANSYS-CFX there are 4 softwares available to do this job. ICM is the one who can do the geometry and meshing job, and CFX3 can do the physics, and there is CFX solver which can solve our problem. Once it is solved, then it generates some result file, and when this result file goes into CFX post, which is a post processing tool, so we can visualize our results. So in the next 2 lectures I will show you how we can solve problem using ANSYS-CFX. So this is where we finish today.